Welcome and hello. This is a video tutorial in HEC RAS, and in this lesson, I'm going to be talking about model accuracy, stability, and sensitivity. This is actually part two. The previous lesson, lesson 37, was part one, but I just didn't get through all I had to say. All right, so what I have on the screen here is my HEC RAS. It's a model, it's a very simple model, but I'm going to be returning to this as needed. What I'm actually going to do to guide this lesson is go to this page here, Model Accuracy, Stability, and Sensitivity, and I'm going to leave a link to this page in the video description if you're interested in following along. All right, in the previous part, part one, we talked about the first two methods of dealing with instability, which was one and two right here, cross-section, section spacing, and computation time step. From here on out, we're going to be dealing with the other methods, the other factors in the model that could improve model stability and or accuracy. Starting with number three, theta weighting, number four, calculation options, and so on. So in this video, in this lesson, if I refer to a list, okay, on to number three, on to number four, I'm referring to this list right here. In part one, I mentioned that accuracy deals with the closeness that the model results provide the user to the true value, and that stability refers to the model's ability to produce consistent and physically realistic results without oscillations or diversions. And what I didn't mention is that between those two attributes, there's somewhat of a trade-off. For instance, you want your model to be stable, but you also want it to be accurate. And sometimes one comes at the cost of the other. I would say that it's more important to have a stable model than accurate. Because if it's not stable, it's not accurate anyway. You want a stable model as accurate as possible. For instance, smaller time steps improves the accuracy, but also leads to a potential of instability. However, numerical diffusion or artificial stability improves stability at the cost of accuracy. A few other factors with regard to HEC RAS and stability and accuracy are the simplification of boundary conditions, parameter value adjustments, as well as the overall model complexity. So as we look through this list and we talk about accuracy versus stability, I just want you to keep in mind that they work together, but oftentimes there is also a trade-off involved. All right, well, let's go ahead and get started with the list here. We're going to get started on number three, theta weighting factor for numerical solutions. So let me just zoom down to theta. Okay, here it is. And I'm not going to just stare at the user's manual this whole video. Let's actually go into HEC RAS and find theta. So to do that, you can go up to the running stick figure running up a hill for unsteady flow analysis button, or you can go run unsteady flow analysis. And then in the options menu, go ahead and select the computation options and tolerances. The first tab here is going to be selected by default. That's the general tab. And then the first couple values are theta. So theta and then theta for warm-up period. The first theta is going to be for the main simulation. And then theta for the warm-up period is for the warm-up period. If you have a warm-up period, currently we don't by default. And those values are going to be 1. I should also point out that the next tab over, 2D flow options, also has a theta and a theta warm period, also with the default value of 1. All right, so 0.6 is the minimum, theoretically at 0.5. The value 1 here is going to provide the most stable but least accurate value for theta. 0.6 is going to be the most accurate but the least stable. So if you have an accurate solution, if you have a stable solution with 1, you may want to decrease your theta values, specifically this first theta value for the main simulation, to get improved accuracy in your results. But you don't want to decrease the value too much, otherwise your model may go unstable. So that's what I mean by there sometimes being a trade-off. If your model is unstable, make sure to set theta to 1. And for rivers with tidal boundaries, in which case rising tide will propagate upstream, use theta of 0.6, that minimum value. All right, on to number 4 on our list is calculation options and tolerances. That's referring to this same dialog box here, but just further down we have the different tolerances for water surface calculation tolerance, storage area elevation tolerance, and then flow calculation tolerance. As you can see, the default values are shown right here of 0.02 feet for both the water surface and storage area. And then max flow does not have a value. That just means that by default, it's turned off. When HEC RAS is computing, it will run as many iterations as possible, as necessary, I should say, to satisfy these particular tolerance values, unless it hits the maximum number of iterations, which is further down here. Generally speaking, increasing these tolerance values will lead to a model that is less stable, but it will be faster when it computes. Decreasing these tolerances will make the model more stable. However, decreasing these tolerances may require more iterations and may result in a slower computation because more iterations are run. As mentioned before, we have this maximum number of iterations between 0 and 40. I think the minimum bound should actually be 1. Anyway, it says 0 to 40. The default value is 20. And then over here in the right frame, the 1D, 2D unsteady flow options frame, these are also computational options and tolerances. For instance, a warm-up period. If your model happens to be unstable, particularly at the beginning of the simulation, then you may want to use this warm-up period. What we have is the number of warm-up time steps. So what you do is go ahead and type in a positive integer here to specify the number of time steps you want your model to use to warm up. The next field down here is the time interval or time period in hours. So for instance, if this is 0 or just left blank, it will assume it's going to use the default computational time interval, which is set for 1 minute for me right here. So 1 minute, if I wanted a warm-up time of, say, 1 hour, then that would be 60 minutes. 60 is the number of time intervals. So I'll go options. Then I would go ahead and set this to 60 right there if I wanted 1 hour. Now, the question is how many time periods, how much warm-up time do you need to give the model? And that's really up to the modeler. I mean, the more time periods, the better chance your model will be stable. However, at a certain point, more warm-up time will not actually improve the chance of stability of your computation. Below that, we have the minimum time step for slicing and then maximum number of slices. So these two fields work together. And what they are is if your flow is rising too quickly, then HEC RAS will splice that time interval into two halves and then again and again as many times as are necessary or as dictated by the limits here. So currently there's really no limit on this first field because it's never going to slice down to 0. And then the maximum number of time slices is 20. That's a large number. So putting values of 0 and 20 here is probably very good for stability. If you wanted to say there's no slicing at all, then you could just say 0 right here. Okay, so I'm just going to return that to its default value. All right, so number 5 on the list is lateral structures and weirs, and that refers to these 4 values right here. The first two are lateral structure flow stability factor and then inline structure flow stability factor. If you notice that there's instability in your lateral structure or your inline structure, whether that's a gate or a culvert or any other structure like a weir, then what you should do is increase the value of these parameters here. So by default, it starts you off at 2 and at 1, and you can see the range is between 1 and 3. So if you get instability, go ahead and increase these values. And if you're already stable and you want to improve your accuracy, then I would slowly decrease these values, but not below 1. The higher the value here, the more the dampening and the more smoothed out the oscillations. So for instance, yeah, obviously one solution here would just be to decrease the computational time interval. But if you've already done that enough and the flow is going to change over the course of that time interval, then increasing the dampening can certainly help stability at the cost of accuracy. The user's manual also mentions that gates should be opened slowly, especially if it's a large percentage of the flow that's expected to flow through the gate, whether it's inline structure or a lateral structure. So that's also something good to keep in mind. All right, the next two down here are weir flow submergence factor, or you can call it a decay exponent. These both start at 1, which is the most accurate but least stable. So if you're getting instability in a situation where you have a weir or a gate that is submerged, go ahead and increase these values to as high as 3. And if 3 is stable, you may want to consider running another simulation with a smaller value to improve accuracy. When you have a weir or gated spillway that connects between a river reach and a storage area, or between two storage areas, and oscillations can occur in either direction. So that oscillation can also get out of control, and then changing this value to a higher number, like 3, can help dampen that oscillation and improve stability chances. Okay, so we're on to number 6 now. This is steep stream and mixed flow regime. I'm going to close this dialog box here, and I'm also going to close this dialog box as well because it's talking about critical depth and how typically in river systems you're going to have subcritical flow. So if you go up to run and then study flow analysis, this is the only place that I could find the flow regime listed. And by default, it will be subcritical. I was in here earlier clicking around, but subcritical will be your solution most of the time. Higher velocities and rapid changes in depth and velocity are more difficult to model and to keep a stable solution. Use subcritical flow by default unless you have a good reason to believe that supercritical flow is involved in your simulation, or mixed flow, which would be a combination of both subcritical and supercritical. But when the water surface passes through that critical depth, then that just proves to be hard to model and is much more susceptible to an unstable solution. So a few things you can do to determine if mixed or subcritical are required is to look at the profile plots. And if the water surface elevation is approaching the critical depth or the Froude number is approaching 1, then you may need to toggle on mixed or subcritical. Mixed, go with mixed. So if I go view and then cross section, and then let me go down to river station 0. Okay, I need to turn on the critical depth here. So options, variables, and then I should have a critical depth for a variable. And boom, this line right here, let me zoom in a little bit. This line right here is the critical depth, as you're seeing from the legend. The blue line here is the water surface elevation. And while I'm zoomed in here on this downstream most cross section, I'm going to go ahead and animate the simulation. I'm going to go up to options, animate, and then just click the play button and see what happens. Okay, so the water surface goes up because of the flow hydrograph, and then it goes back down. But at no time does the water surface elevation ever cross or even touch or come close to that critical depth. So in this situation, this is a very stable model. I don't need to consider that. But if your water surface elevation approaches that critical depth or touches it completely, that's when you may need to change the flow regime to subcritical or mixed, and then change a number of the other parameters in your model to accommodate a potentially more unstable model as a way to prevent instabilities. If we go up to the data and we go view results profile summary table, we have the Froude number right here. It's 0.64, so that's safely in subcritical zone. We were only looking at this last cross section right here at river station 0. We're at 0.64. But if I want to toggle on all the time periods, I can go to options and then profiles and then select all, remove the max, click OK. And now this is all for the top cross section. So let me scroll down to the bottom cross section here. That looks good. And then this is the start of the simulation. And then this is as the flow rate increases, we see the Froude number here is 0.63, 0.64. It gets up to 0.78, it looks like, 0.77 right there. And that's the closest it gets to 1. So we're pretty good. It's just another way to look at numbers as opposed to a plot when trying to determine if the subcritical flow is going to turn into a supercritical flow. So close this. Anyway, the solution to that situation would be to click on mixed flow if you're going to be going supercritical. A few other solutions that the user manual provides is to increase Manning's N value, which effectively serves as the friction, and then also to increase the hydrograph's base flow value. That way, it will dampen out water surfaces going towards or through critical depth due to low flows. All right, we're on to number 7 now. This is downstream boundary conditions. So this is similar to upstream conditions and the critical depth. What we want to do is if the downstream end of the water surface elevation is approaching critical depth, you may also experience instability in your model. If I go up to view and then water surface profile, okay, I've got all the profiles toggled on here. Let me go up to options, profiles, and then clear all. Let's just go with the first profile right here. All right. So I'm not seeing the critical depth. I see it in the legend, but I think it's only for the downstream most cross section. If I want that variable to appear, let me make sure it's toggled on. I think it is. Variable and then critical depth. Yeah. So if I toggle it off, it's gone from the legend. I want it to be turned on. So I'll go variable, critical depth, elevation. and I'm not seeing it in the plot here. I can zoom in just by going options and then zoom in, and then let's take a look at it here. Yeah, so there's a little tiny red tick mark here. I don't know if you can see that, but that represents critical depth. What I want to see is critical depth along the entire reach here. So what I'm going to do is go back to, I believe it's in here, steady flow options, and then click on critical depth output, check it on. Critical depth always calculated, so that should be for all the cross sections as well as the interpolated area between the cross sections along the reach. I'm not sure if that control exists over an unsteady flow or not, but let's go ahead and run it now. Compute. So let me close that. Let me now check that cross section. So we'll go view, water surface profile. Okay, so it's there now for some reason. Let me go ahead and zoom in. By the way, another cool way to zoom in I just found out is to drag along the axis itself. So if I want to zoom in on 206 down to 202 vertically, so I can just drag that right there and then boom. Also, I can zoom in on the horizontal axis. I'll just say from 0 to 1500. So you just drag and then boom. All right, anyway, I thought that was cool. What we have is the water surface elevation above the critical depth. The problem with instability could occur if the water surface elevation abruptly jumps the downstream end of the river reach or it abruptly dips, especially if it dips down below this critical depth line. This can lead to an unstable solution that can propagate upstream in later time steps. One solution is that the slope of the downstream boundary condition may be wrong. So for instance, if the slope is too steep right here for the friction, that may result in a dip below critical, or if it's too flat, then that may lead to an uptick in the water surface elevation, which would be unnatural and also propagate upwards. So to set that, you go up to edit, unsteady flow, and then for the downstream boundary condition, which I have here at river station 0, just go ahead and double click that, or you can just select it and click normal depth. Right now I have it set to 0.5% or 0.005 is the decimal notation, and that is equal to my channel depth. So I just usually use normal depth as a downstream boundary condition and set it to the normal longitudinal channel slope in my model, and I've never had a problem with that. Okay, we're going kind of long in this lesson, so let's just do one more. This is number 8 now, cross-section geometry and table properties. So the problem here would lie if the hydraulic properties table have an abrupt change to their value, such as the flow rate or the conveyance, that's flow rate, or storage with a small change in elevation. So let me open up the cross-section here real quick. What I'm referring to would be like this overbank station, or most notably, it would be if there's a large storage area that's off stream, and then some ineffective flow area was preventing water from flowing into that large area. This is common during levee overtoppings where a large ineffective flow area becomes effective as the water surface elevation rises above the set ineffective flow elevation. Now, I don't, this cross section wouldn't have that problem, but if I had a large ineffective flow area over to the side with lots of storage, there would be a couple solutions to that. And one solution would be to model that storage area as a separate element, such as a storage area element. You could just go ahead and sketch out a large storage area, use that instead of part of your cross section. So this is not part of the cross section, but is part of a storage area. Also, the ineffective flow area that you do use could be set to permanent. You could check the checkbox for permanent on if you go ineffective flow area and then check the permanent checkbox. And then the last solution offered is to not let the hydraulic properties change so abruptly. So the solution to that would be if you go to your H tab param, your hydraulic properties parameters here. Here I have 4 cross sections in my river reach. And right now, let's just focus in on this bottom cross section. It has an invert of 200. The starting elevation is 200.5. And then every 0.38 feet vertically, it has a new cross section. But you may have a problem at this overbank, or more likely if you had some sort of levee situation with a lot of storage off to the side in an overbank with non-permanent ineffective flow areas. Anyway, the solution here would be to make more vertical lines, more lines so that there's just more detail in the hydraulic properties tables. To do that, you can just go ahead and edit this. So whichever cross section I have selected is the one that I'm editing. starting at 200.5. So what if I started at 200.2, and then for the increment, I could change that to 0.2. It hasn't quite updated the image yet, so there we go. If I click off and then click back on that row, it updates the image. But at 0.2, well, if we're only using 20 points, it only goes up to here, about 204. So let's go ahead and increase that. I'll just change the 20 to 40. And then it hasn't updated yet, so let me click off and click back on. And it looks like 40 is sufficient. So now the vertical discretization is twice as much, and the hydraulic properties tables will have less change in area and flow rate and all those other parameters that these hydraulic properties tables are used for. And that's another way to reduce the chance of instability. All right, well, we got through number 8 on the list. Here's the list again. Here's the last one we finished up with. So in this lesson, we talked about theta weighting factor number 3 all the way down through cross-section geometry, tables, and properties as a way to reduce the chance of instability in your models, but also try to preserve as much accuracy in the process.